There is a moment in every war when an army stops believing its own weapons are enough. For Germany, that moment came not in a conference room, not in a defeat, but on the open ground of the Eastern Front in the summer of 1941, when a Panzer III shell bounced clean off the hull of a Soviet tank that wasn't supposed to exist. The T-34 wasn't just better in some ways. It was better in the ways that mattered most. And Germany, to its credit, knew exactly what to do next. It took the thing apart. What follows is the story of every major weapon and vehicle that Germany reverse-engineered from its enemies during World War II. Some of these copies matched the original. Some surpassed it. And a handful of them, Germany never cracked at all. That last group tells you just as much as the first. Chapter 1. Steel that fought back. The Eastern Front's greatest lesson. Operation Barbarossa launched on the 22nd of June, 1941. In the first weeks, German panzer divisions moved faster than any army in history, and the world watched in something between awe and terror. But on the ground, in the dust and mud of Western Russia, something was going wrong. The standard German anti-tank weapons weren't working. The 37mm gun on the Panzer III, the backbone of the armored force, was bouncing shells off a Soviet tank that weighed 26 tons, rode on wide tracks, and carried armor that wasn't just thick, it was sloped. The tank was the T-34, and Germany had no intelligence on it whatsoever. By the time Barbarossa launched, the Red Army had nearly 1,000 of them in the field, and Germany's tank crews had never seen one before. General Heinz Guderian, the most accomplished armored commander in the Wehrmacht, didn't need long to reach a conclusion. He sent a formal recommendation to the High Command in late 1941. Copy it. Not study it. Not draw inspiration from it. Copy it, part by part, as closely as German industry could manage. That proposal was modified, but it was never entirely rejected. In November 1941, a special commission of engineers and panzer officers traveled to the Eastern Front, specifically to strip down captured T-34s and record everything. They focused on three things above all else: the sloped armor, the wide tracks, and the 76.2mm gun that could kill a Panzer III at 1,000 meters. The sloped armor was the revelation. It wasn't the thickness that made it so difficult to penetrate. It was the angle. A round, striking armor at 60 degrees doesn't transfer its energy cleanly. It skids, deflects, or shatters. The T-34's hull front gave incoming rounds a problem they couldn't solve, and the Germans knew it. The tracks were the other breakthrough. At 500 millimeters wide, they spread the tank's weight across a footprint that kept it moving in conditions that turned German panzers into stuck metal boxes. The autumn mud of Russia, the spring thaw, the deep snow of winter, the T-34 kept going. Two German companies received contracts to produce a new 30 to 35-ton tank in response. Daimler-Benz submitted a design so similar to the T-34 that photographs of the wooden prototype alongside the Soviet tank are striking even today. Diesel engine, rear drive, leaf spring suspension. It was close to a copy. The other contender, from MAN, took a more traditional German approach, but absorbed the same lessons on armor and mobility. MAN won the contract. The result entered service in 1943 as the Panther tank, and it was a machine that owed its existence entirely to what Soviet engineers had built in Kharkov 4 years earlier. But Germany didn't simply copy. It improved in the places where German engineering traditionally excelled. The Panther carried a 75mm KWK-42 gun that could penetrate T-34 frontal armor at over 1,900 meters, nearly double the effective engagement range of the Soviet weapon. The turret gave its commander a full 360-degree cupola. The Zeiss optics were superior to anything the Soviets were fitting in 1943, and the five-man crew layout meant the commander wasn't doubling as the loader, which was the T-34's notorious blind spot in close combat. The Panther weighed 45 tons by the time it reached the battlefield, almost twice the T-34's combat weight. That was the German failure, not in the engineering of the copy, but in the restraint they couldn't manage. The lesson was absorbed. The discipline was not. A very different kind of lesson arrived from the same front, just 3 weeks after Barbarossa began. On the 14th of July, 1941, near the town of Orsha in western Russia, a small battery of 7 Soviet rocket launchers opened fire on a German supply depot. The attack lasted under 10 seconds, 112 rockets. The depot was destroyed. The weapon was the BM-13 multiple launch rocket system, soon known to every German soldier on the Eastern Front by the name they gave it themselves, Stalin Orgel, Stalin's organ. The sound was the thing, a shrieking, howling wall of fire with no warning at all, and the after-action reports from Wehrmacht units who survived their first encounter make it clear that the psychological effect was as damaging as the physical one. The Soviets treated the Katyusha, as their own troops called it, as one of the most tightly held secrets of the entire war. NKVD security detachments were posted specifically to guard the launchers, with standing orders to destroy them before capture. The crews were briefed on what to do if surrounded. The system was that important. Germany couldn't get a clean copy, but it got enough. By 1942, the Waffen-SS had reverse-engineered the Soviet 82mm M8 rocket and produced a German clone at 78mm caliber, scaled down slightly to fit German launcher hardware. The German version was fired either from captured Katyusha trucks or from specially built launchers mounted on captured French Somua half-tracks, which gives some sense of how layered and improvised Germany's response to Soviet rocket technology actually was. More broadly, the encounter with Soviet salvo artillery pushed Germany to scale up its own Nebelwerfer program dramatically. The 300mm Schweres-Wurfgerät 41 appeared by the end of that same year, a direct product of watching what massed rocket fire could do to an army in the open. Chapter 2. The rocket that crossed the Atlantic, from bazooka to Panzerschreck. The American M1 bazooka was not a sophisticated weapon. It was a steel tube, a rocket, and a trigger mechanism that a trained soldier could fire from the shoulder. Robert Goddard, the American rocket pioneer, had worked on the core concept during the First World War. By 1942, the U.S. Army was issuing it to infantry units and also shipping it in large quantities to Soviet forces under Lend-Lease. Germany first saw the bazooka in North Africa in late 1942, when advancing forces overran Allied positions during the Tunisian campaign and found examples among the captured equipment. More came via the Eastern Front, picked up from Soviet units. Either way, what mattered was what German engineers saw when they took one apart. Here was a weapon that gave a single infantryman the ability to kill a medium tank. A handheld anti-armor solution that needed no crew, no carriage, no towing vehicle. Its 60mm shaped charge could penetrate enough armor to destroy most German tanks from the side. The concept was irresistible. Within months, Germany had a program underway to produce its own version. The result, the Raketenpanzerbüchse 43, entered service in 1943. The troops renamed it immediately Panzerschreck, Tank Terror. Some called it Ofenrohr, the stovepipe, which tells you something about what it looked like. But Germany didn't copy the dimensions. It improved the caliber. The Panzerschreck used an 88mm round against the bazooka's 60mm, and the result was a warhead capable of penetrating 210mm of armor. That was thicker than the frontal plate on any Allied tank in service at the time. On that single metric, the German copy was in a different category from the American original. The trade-offs were real. The Panzerschreck weighed 11 kilograms against the bazooka's 6, and the rocket motor was a problem. In the bazooka, the propellant burned out entirely inside the tube, which meant the operator needed no special protection. In the Panzerschreck, the rocket kept burning for about 2 meters after leaving the muzzle. Operators were officially issued gloves, a rubberized poncho, and a gas mask with the filter removed, just to fire the weapon without being burned or gassed by their own round. The improved RPZB-54 model, which appeared in February 1944, added a curved steel blast shield to the front of the launcher. This helped, but it also added weight. The weapon was never as handy as its American predecessor, but in terms of raw anti-armor capability, it was a different class entirely. Over 314,000 Panzerschrecks were produced before the end of the war. For a weapon that was essentially a foreign design scaled up and recalibrated, that production number reflects how badly Germany needed what the bazooka had proved was possible. Chapter 3: Signals Stolen from the Sky. The Battle for Centimetric Radar. Britain's greatest secret of the entire war was not a code and not a battlefield weapon. It was a copper cylinder about the size of a dinner plate. The cavity magnetron, developed at Birmingham University in 1940, made it possible to generate radar waves at 10 centimeters wavelength. The previous limit had been around 50 centimeters. That gap sounds small. Its effects were enormous. Centimetric radar produced images with genuine resolution. A navigator in a bomber could now look at a radar screen and recognize a coastline, a river, a city. An anti-submarine aircraft could detect a U-boat's periscope. A night fighter could find a bomber in total darkness at a range that made interception reliable rather than lucky. The magnetron made all of this possible, and it fit inside an aircraft, which was the other part that mattered. British authorities debated for months whether to risk flying it over German-held territory at all. The concern was specific and documented. The magnetron's core component was a solid block of copper. If a bomber carrying one was shot down over occupied Europe, the block could survive the crash intact, and whoever found it would know exactly what it was. They used it anyway, and on the 2nd of February 1943, an RAF Sterling bomber on a covert test mission over the Dutch coast was shot down near Rotterdam. The H-2S bombing and navigation radar it was carrying, the first operational system built around the cavity magnetron, was recovered by German forces in near-perfect condition. What happened next is one of the more striking moments in the technological history of the war. German engineers pieced the device back together and used it to display an image of Berlin on a laboratory screen. The reaction, by multiple accounts, approached panic. The Luftwaffe had known the British were developing something new in radar. They had not known it was this. Their own best ground-based tracking systems, the Würzburg series, operated at 50 centimeters. Britain had jumped to 9.7. Germany was not catching up. Germany was years behind. AEG Telefunken was tasked immediately with building a German equivalent. The captured device was codenamed Rotterdam by German scientists, and the reverse-engineered German version became the Berlin radar series. Produced at 9 centimeters, it was developed in 4 distinct variants. The FUG-224 Berlin A was a ground mapping radar. The FUG-240 Berlin N1 was an airborne interception set for night fighters. The Fumo 81 was a naval version. The Fumo 83 and 84, known as Berlin 1 and Berlin 2, were built for U-boats. German naval engineers who worked on the Berlin series later noted in their reports that the German copy was better engineered than the British original, lighter and smaller for equivalent performance. The British had solved the physics first. Germany solved the engineering better. That combination produced the most capable centimetric radar system operational at the end of the war. But the Rotterdam find didn't just give Germany a radar. It also told Germany what it had been missing. The Naxos radar warning receiver, introduced in September 1943, was built specifically to detect transmissions from the British cavity magnetron. It operated between 2,500 and 3,750 megahertz, covering the exact band the magnetron used, and it gave U-boats a detection range of roughly 8 kilometers against aircraft, carrying H-2S-derived radar. 8 kilometers was enough to dive before the aircraft could lock on. The Naxos was built by Telefunken using modified components from existing IFF equipment, which meant production could start quickly. The first operational sets reached U-boats in September 1943, less than 8 months after the Rotterdam aircraft went down. For a reverse-engineered technology requiring fundamental electromagnetic engineering, that timeline was extraordinary. Chapter 4. Under the Atlantic, Torpedoes, Submarines, and Stolen Silence. Germany entered the war with a torpedo problem. The G7A steam-powered weapon left a visible white wake, which meant ships had warning. The G7E electric version solved that, but it had a depth-keeping defect that caused many early torpedoes to run too deep and pass harmlessly beneath Allied hulls. In the first months of the war, U-boat crews reported misses on targets that should have been impossible to miss. German engineers fixed the depth problem. What they couldn't fix, and what they could see the Allies solving around them, was guidance. A torpedo that runs straight is easy to avoid once you know it's coming. A torpedo that hunts you is something else entirely. Britain had been working on acoustic homing torpedoes, a concept driven by the simple observation that a ship's propellers produce a distinctive noise signature. If you could build a device sensitive enough to track that noise and steer toward it, you had a weapon that did not require precise targeting. German naval intelligence tracked this development closely. The British work accelerated Germany's own program for the T-5 Zaunkönig, the Wren. The T-5 entered service in September 1943, designed with one specific target in mind: Allied escort destroyers and destroyer escorts, the ships that were killing U-boats in steadily increasing numbers. Point it at a convoy screen, set it running, and let it find the propeller noise on its own. In its operational debut, during the battle around convoys ONS-18 and ON-202 in September 1943, T-5 attacks sank 3 Allied escorts in a single engagement. The Allies' response was the Foxer, a noise-making device towed astern that generated a propeller-like signature and pulled the homing torpedo away from the hull. Germany's counter was to modify the Zaunkönig's acoustic filter so it could distinguish between a real propeller and a decoy. Then the Allies changed the frequency of the Foxer. Then Germany adjusted the filter again. The cycle ran until the end of the war, a closed technical loop between 2 engineering establishments that never stopped learning from each other. Something very different arrived from the Netherlands in May 1940. when German forces occupied the country and found something unexpected aboard a Dutch submarine, a breathing tube that allowed the vessel to run its diesel engines while fully submerged. The Dutch called it a snorkel. Germany examined it, catalogued it, and then largely ignored it for 3 years. By 1943, with Allied radar and air cover making surface operation nearly suicidal, the snorkel became critical. Germany developed its own version and began fitting it to operational U-boats in 1944. It was not a glamorous reverse engineering story. It was the story of a solution sitting in a filing cabinet for 3 years until the war finally made ignoring it impossible. The entire arc of the Battle of the Atlantic shaped the last and most ambitious submarine project Germany produced. The Type 21 U-boat was not reverse-engineered from a single captured weapon. It was engineered as a response to everything Germany had learned about Allied anti-submarine capability: radar detection, depth charge patterns, air coverage, convoy escort tactics. The key specification was a submerged speed of 17 knots, sustained. That meant battery capacity far beyond anything previous, and a streamlined hull that sacrificed nothing to surface performance, because surface performance was now dangerous. The Type 21 was the first submarine designed from the outset to live entirely underwater, and it was built around fear of what the Allies had built above it. Chapter 5. The Ones They Never Solved. Not every story in this history ends with a working copy. 2 of the most instructive cases are the ones where Germany captured enemy technology, studied it with the full resources of its engineering establishment, and still failed to reproduce what it had found. The first was the bouncing bomb. On the 16th of May, 1943, 19 Lancaster bombers of 617 Squadron crossed the Dutch coast at low level and attacked 3 of Germany's most critical industrial dams. The weapon they carried was unlike anything Germany had seen. A cylindrical drum spun to 500 revolutions per minute before release, dropped from 60 feet at precisely 232 miles per hour, and designed to skip across the surface of the reservoir, like a stone skimmed across water. When it reached the dam wall, the backspin pulled it down against the face, and it detonated at depth. The Möhne and Eder dams were breached. The flooding killed over 1,600 people and wiped out critical infrastructure across the Ruhr Valley. Germany immediately began a program to replicate the weapon, internally designated Kurt. Engineers recovered bomb fragments from the raid sites and from crashes. They understood the shape. They could estimate the dimensions. What they could not identify, because it was not visible in the wreckage and was not obvious from first principles, was the backspin. The rotation that made the bomb stable across the water, that gave it a predictable skip trajectory, that pulled it down against the dam face at depth. Without knowing that a 500 revolutions per minute backspin was the core of the mechanism, every German test version broke apart on impact or flew off course. They tried fitting booster rockets to stabilize the trajectory. The rockets introduced their own failure modes. The program absorbed time and resources and produced nothing that worked. Kurt was eventually abandoned. It is one of the only cases in the war where Germany understood exactly what a weapon had done, captured physical evidence of how it was built, and still could not reconstruct the principle behind it. The second failure was more humiliating, because Germany literally held the answer in its hands. The American VT proximity fuse was one of the most closely guarded secrets of the entire war. Its importance was considered comparable to the Manhattan Project and to the D-Day invasion plan. The fuse contained a miniaturized radio transmitter inside the shell casing itself. As the shell passed within lethal range of an aircraft or of enemy personnel in the open, the transmitter detected the reflection of its own signal and fired the detonator. No timer, no calculation, no luck required. The Pentagon refused to authorize its use in land artillery for years, specifically because of the reverse engineering risk. If Germany captured intact examples and understood the mechanism, Allied bomber formations could be made catastrophically vulnerable. In December 1944, during the Battle of the Bulge, German forces overran an American ammunition dump and captured approximately 20,000 proximity-fused artillery shells, the largest single haul of the secret technology of the entire war. German engineers examined them. They opened the casings. They looked at the components. And they concluded that what they were looking at could not be what it appeared to be, because they had already determined that a radio-triggered detonation mechanism could not survive the acceleration forces of a gun firing. The physics, as they understood it, ruled out the possibility, so they dismissed what they held in their hands. Germany had in fact been independently developing over 30 different proximity fuse concepts throughout the war. Acoustic fuses triggered by engine noise, electrostatic designs, radio variants. None of them reached service. The miniaturization problem that the Americans had solved at enormous cost, using production capacity from more than 100 companies simultaneously, was the barrier Germany could not cross. And when the Americans handed them the finished solution in a captured ammunition dump, German engineers looked at it and decided it must be something else. The proximity fuse stands alone as the clearest demonstration that reverse engineering is not just a matter of having the object. It requires understanding what the object actually is. Chapter 6. The Long Loop, when American weapons came home through Soviet hands. There is a final irony in this story, and it concerns a weapon system that Germany encountered on the Eastern Front, but that had started its journey in the United States. The Lend-Lease program shipped an extraordinary volume of American military equipment to the Soviet Union. Trucks, radios, aircraft, food, and weapons. Among the weapons were M1 bazookas, which reached Soviet infantry units in substantial numbers from 1942 onward. When German forces overran Soviet positions, they found American equipment. Some of it was already familiar. Some of it pointed to something new. The bazooka that started the Panzerschreck program came through this channel as much as through North Africa. The rocket launcher that became the most widely produced German anti-armor weapon of the final 2 years of the war was, at its origin, an American design that had crossed the Atlantic, been issued to Soviet soldiers, been captured by German forces, been taken to German laboratories, been enlarged from 60 millimeters to 88 millimeters, and been put back into production in German factories. That journey, from Ohio to Moscow to Tunisia to Berlin, describes the nature of technology in a global war more precisely than any single weapon could on its own. Nothing stayed in its lane. Nothing belonged only to the side that invented it. Everything traveled, and everything became something new in the hands of whoever picked it up next. Chapter 7. The Engineering Verdict. When you add it all together, the scale of what Germany accomplished in reverse engineering is remarkable. It happened faster than peacetime development cycles, under constant material pressure, with access to fragments rather than blueprints, and with engineering staffs that were already stretched across dozens of simultaneous programs. The Panther tank took the T-34's core insights and built a more capable fighting vehicle around them, one that outranged its Soviet counterpart by nearly a kilometer and gave its crew an ergonomic and optical superiority the T-34 never matched. The Panzerschreck took the bazooka concept and produced a weapon that could defeat armor the original couldn't touch. The Berlin radar series took a cavity magnetron recovered from a crash site in the Netherlands and produced centimetric radar equipment that German engineers themselves judged to be better made than the British original. The Naxos receiver gave the U-boat fleet a defensive tool against the technology that had been sinking it in increasing numbers. The T-5 Zaunkönig brought acoustic homing to operational use and forced the Allies into a counter-development race they didn't fully win before the war ended. The Schnorkel, borrowed from the Dutch and scaled to German submarines, fundamentally changed how U-boats operated and survived. And then there are the failures. Kurt, the bouncing bomb that Germany almost understood. The VT proximity fuse, which Germany literally held in its hands at the Battle of the Bulge and could not read. The Katyusha clone that worked, but only as a shadow of the system that had inspired it. Taken together, what Germany's reverse engineering programs reveal is not a picture of strength. They reveal a picture of reach exceeding grasp, of an industrial and military machine that had committed to campaigns it could not supply and timelines it could not meet, and that spent the middle and final years of the war frantically building copies of what its enemies had already solved. The engineers who did this work were talented by any measure. In a number of cases, they produced results that were genuinely superior to the originals, but they were always responding. They were always behind. And in a war where the margin between response and initiative is measured in armies, being behind is where it starts to end. The weapons that Germany copied tell the story of a nation at war with more of the world than any industrial base could manage. The ones it couldn't copy tell a smaller and quieter story about the limits of engineering under pressure and about the gap between capturing a secret and understanding it. Germany drove whatever it could find, and it built whatever it could reverse engineer. And in the end, it wasn't enough.